Good morning, everyone, and welcome to this Railmonitor webinar about today's topic is dynamic trackbed geometry monitoring for predictive maintenance. Thank you, everyone, for participating. I would just like to start by introducing who is present on our side. We have Christina, who's our marketing responsible person, and she has actually the one who's produced most of the material that we are going to see today. Myself, I'm Christian. I'm CSO at Railmonitor. I've been here for about 2 years, so in charge of sales. We have Niels, who is going to be moderating most of today's session. He's one of the founders of the company and is also our chief technical officer here. And last but not least, we have Morten, who is a new member of our sales team. He is joining forces with me to run our sales.
Okay, I'll just go through a few housekeeping for the webinar today. This session will be recorded and shared afterwards. You're more than welcome to ask questions. Please write them in the Q&A chat, and then we will get back to them at the end. If you have questions at the end, you can just raise your hand, and then I will unmute you so that you can also ask the question. If there are questions we do not get to, we will get back to you after the webinar too, so that all questions get answered.
Well, just very quickly, today's agenda. First part we already did. Then in just a few seconds, Niels will come in and he will showcase dynamic track with deflection. He will do a live demonstration for you, for all of us. And then, as Christina said, we will do a Q&A session at the end, and we will also have some additional information for you at the end of today's webinar. So, Niels, go ahead.
Thank you, Kristen. Hi, everybody. So before we are diving into today's webinar topic, we just have to align some foundation of a normal track. Its primary function is to provide a stable and durable base for distribute the loads of the passing, and also maintaining a proper track alignment, and also ensure a safety and smooth operation. Besides this, the track bed also helps to drainage and prevent the track deformation and absorbs vibration from the train movement. Due to its construction using the ballast, the track is also able to move in a natural way vertically, and it's also able to absorb the temperature changes, the load, and also the ground movements. The maximum size of the vertical movement is typically allowed due to various depending standards, and also specified for the train speed and the load. So that is more or less the foundation for today. As we are going to talk about track deflection and monitoring on these, we are today focusing on the track in zones where the supporting structure consists of different materials. So we have a ballasted zone, and we also have a zone where there is other material, like, for example, in a bridge or a slab track. And the focus here is the approaching zone, which is the end of the ballast zone. In the new tracks, these zones are carefully constructed to make the transition between the ballast and this concrete or bridge crossing as smooth as possible. However, in many transition zones, they do not have these. And since also loads become more heavier and the train speed also increase, the amount of train also increases, the sleepers are further exposed. So we have these what we call void issues. This is a localized loss of support between the ballast and the sleeper, the sub-ballast and the subgrade. This is what we see here in the picture. There are some air around the sleepers, and this is typically here in this what we call the approaching zone or the transition zone. The cause of this is that the track will start pumping or moving more and more, and this will of course also affect the degradation of the ballast, and also over time the rail. The location is typically, as said before, critical in the transition zone between these different structures of the ballast and the concrete. It could be in embankments, but also in tunnel portals. So what will this impact? Well, overall, the most risk is that we have, of course, the loss of track geometry, which will influence the safety challenges. And we have the dynamic loading. The wheels strike the unsupported sleepers and create impact forces to accelerate fatigue failures. We have some called derailment risks. It's a severe and uncorrected void. These can increase the lateral forces, and the track gauge might also change. In interfaces with bridges, the transition will also abrupt stiffness and change to have these hanging sleepers, which actually magnify the void problem. If you are a passenger in the train, these voids also affects the passenger comfort. They would maybe experience more vibration when the train passes over these voids. There might also be more noise and vibration, which also leads to change in the passenger comfort. For the lifetime and the asset management life, there will be also an accelerated wear. These repeated impact accelerates the rail corrugations, maybe also sleeper cracking, and the ballast will also be crushed and then not have these elastic absorptions anymore and be more stiff. There will be some maintenance burden, more frequent tampering, maybe also stone blowing and under sleeper stabilization. So these are all things that are being challenged by having these voids. Of course, from the construction side, we are trying to avoid these, having these stabilized. But as said before, we are facing that old tracks, they are having these issues. Especially in the transition zones, where we have these ballast, as you see here, and we have a bridge, and we have ballast on the opposite side. What you see here is actually a situation where we have installed sensors on both sides of this bridge to monitor these voids, and being able to actually notify if the voids are being heavier over time. For these voids here, this is typically 1 to 2 meters ahead from the bridge on each side, and this is where the location of the monitoring should be placed. These zones, of course, often needs to be taken care of and require a more repeated intervention, and this is something that we have focused on. And instead of having measurement train running more frequently, it is possible to have a system like a monitoring system for void monitoring installed. So, going more into detailed, we have these. We have a system that are where we install sensors in the track. There are different ways of installing these sensors, and I will go into the more detail why it can be put in the track in different, I would say, options. In this case here, we are focusing on the void monitoring, meaning the deflection of the track when the train is passing, but also static track geometry like cant and twist. In this case, we are placing the sensors on the first part of the stiff element, which is the bridge on both sides, and then on the sleepers next to the bridge in the transition zone. And this is the setup that you will see here in the moment. So here we have two tracks. We have a bridge, a small bridge actually. They're having some issues in the transition zones where they are experiencing more voids. In this case, they're also doing some construction next below the track, and they would like to monitor the voids and also the static track geometry in a more project-based. This is a project of 3 months, so the sensors are installed and the system is up running immediately. In this case, the sensors wakes up when the train approach and monitors the movement, the deflection of the track, and report it to our digital service platform. And it's possible by then to have an alert for if they increases significantly. This is a small video of the same site. We're trying to run it, and hopefully you will be able to see it if the performance of the internet will allow us to do it. So as you can see here, the track is moving downwards, and the sensors will of course monitor these movements. The sensors are wirelessly connected to a gateway, and then will report its maximum movement every time a wheel is actually deflecting the rail. And in this case here, this was a freight train, and we will get the data, and the data will be analyzed in the software. The case we will make a deep dive into today is a little more complex, because in this case, the sensors, as you can see here, is not only placed in the inside of the track, it's placed on the outside of the rail. And the reason for this is because the infrastructure owner here would like to have not only the voice, which means the deflection of the track, but also the possibility to have the information of the dynamic track geometry. If you imagine that we have a sensor in the middle, we will only be able to monitor the movement of the sleeper in the middle. Having a sensor on both sides, we will be able to monitor if both sides are moving exactly the same. And if they are not moving exactly the same, then over time there might be a risk of having a dynamic cant and also a dynamic twist situation, which might cause a risk and safety risk for the train to approach. And this is a very important thing in this case. Here we are talking about a temporary bridge, a bridge that are temporarily installed, and it's very important for the track, for the infrastructure owner to know if the track next to the bridge are stable. And the overall goal here is actually to keep up the speed of the train normally it's only allowed to run 80 kilometers across such a temporary bridge. But having a monitoring system, monitoring the dynamic track geometry, they are then able to run up to 160 kilometers per hour. So this will also impact, of course, that they do not need to change the timetable. They can keep up the customer satisfaction. So this is not just to monitor instability, it's also to actually put value to the passengers, even though that they have some construction sites and some construction work. This is the picture for this case. As you can see here, the sensors are installed on outside the track, here on the bridge, and then on the ballast in the transition zones. And the same goes from the opposite side, and also the track next to here. So we have 2 tracks in east and west position. I will now show you a video, and I also hope here you are able to see that the track is actually moving and being deflected by the train approaching. So here the movement looks very quite heavy. The track is moving approximately 10 millimeters in this case. And in a few minutes, we will have this view in the software as well. For this data, we have seen here that this is the data from these sensors here. The sensors are placed in position 0, which is on the bridge. Position 1 is this one here, and then 2, 3, and 4. And what you can see here is actually the deflection of the track week by week. This is 4 weeks of a monitoring, and week 1, the track is not deflected at all. And then week by week, the track in the transition zones here next to the bridge is moving down to approximately 6 millimeters. And this is very interesting, and also what they would expect. If we then look at the entire monitoring situation here, we will then be able to see how the deflection is on all sensors. And it's very easy to see that the deflection on the bridge is not very much. It's only well, we have rain here in Denmark, so maybe you can hear that as well. I'm not sure about that, but I'm trying to speak a little bit louder. Here we have to see how the deflection is week by week on all the transition zones. And it's very easy to see that the week by week that there will be a void in these areas here. And this is approximately 6 millimeters on this side here, and on the opposite side, it's approximately 10 millimeters. So it's very easy to see how the deflection will increase over time. And in this situation here, the infrastructure owner and contractor made manually track adjustments. So they did a manual tampering process. And this is something we also in a short minutes can see from the data. So you should imagine that this is a construction site. They're installing the bridge for a temporary period. We're installing the sensors, and the sensors are then reporting the data to the software and the Railmonitor trackbed system. This is another view of more or less the same situation. Here we are all small dots here, are trains that are approaching the sensors. And we see very easily that in the beginning of the monitoring period, which was in December last year, we have more or less 0 deflection. And then 1 month later, the deflection is approximately 10 millimeter. Then decided to make a manually track adjustment, and they actually, the deflection again comes to 0. And then maybe 1 month or 1.5 months later, we are still more or less at the same deflection size, meaning that the effectiveness of the tampering is better, but not good enough. They made a new manually tampering, and the story tells the same again. But if we look at the how fast the deflection actually becomes or increasing again, you can see that using these lines. So here we have, this is the first period, this is the second period, and this is the last period. And if you look very carefully, it's possible to see that the angle of this line changes over time, which means that the effectiveness of the ballast or the track adjustment is getting better and better. So the deflection becomes not that steep or increase that much over time every time they did this new track adjustment. On the opposite side, every time you do a track adjustment, you might also crush the ballast, which also could indicate that instead of having these elastic ballast, it might also be that it's because the ballast is more stiff, and you will not see the huge deflection. But this is something that we have not made any further analysis into. But it's just to show you here that using the system, the trackbed 360 system, it is possible to have a more digitalized way of having this trackbed monitoring, and also have a view of how the track behaves when train approaches. As you also can see here, there are also dots down to 30 millimeter. This is because of heavy rail, and this is but we do not consider these as outliers because they are there. But in overall, we concentrate us on the average movement of the track. So now I will have a live demo of how the same situation as you saw before, and I will now move into the digital service platform that we also have is a part of the entire solution. The solution is sensors being installed in the track, and also the software, having access to the software where the software do the analysis of the data and also the presentation, but also of course the conclusion. And to be honest, you do not need to go into the software every day. You only need to pay attention when you get a notification. So then you are able to approach the system and get a more deep dive into the data and have some more information on the decision making. But I will now stop my sharing here, and I will share my screen, another screen here, 2 seconds. I hope you're able to see this. Great. So this is actually the data you saw before. This is from the beginning of March, and the beginning of December last year, and due to April this year. This is all the dots here, as you saw before, is every train that have been monitored, and the data are being sent to this to the software platform here, the detailed service platform. And the blue line in here is the average, and here we see that the tampering is taking place, and the data goes up to the 0 again. Then we have a period of time where the deflection starts to increase down to approximately 6-7 millimeters, and then again a manual tamping process, and then we have the same situation again. So this is how the data is being analyzed, and this is actually the data that we are getting from the sensors. Another way of looking at this and is to have a 3D map, and I will see if I can share this 2 seconds. So this is something that I have been prepared in advance. We have different ways to get into the more detailed data. This is what we call a 3D view. This is the data, the date from the beginning of December until April this year. Here we have the position of the sensors in meters. 10 meters is at the bridge. So the bridge here is 0, more or less, and this is 12 meters ahead from the bridge, more or less the same as you saw before. We see that in this area here, everything is stable. There's no deflection, even though that there are both public train and heavy train passing. But in this area here, which is the transition zone, we see that there are more movement and deflection of the track. If we then turn this 3D graph a little, it's very easy to see that in the beginning of December, the deflection is more or less 0, and then it starts here to deflect down to approximately 6 millimeters. Then we have the tampering process, and then again a period where the deflection becomes increases, and a tampering process, and again. So this is another view, and we can look into the what we call the average, and I will just show you this. This is also what you saw in the presentation before, but here live data that we have. The blue bar here is the last year in week 49, and then we have week by week. This is in German, but week by week the deflection that becomes more and more severe in this area here. So this is an interesting way of looking at the data, and what is it that the infrastructure owner and also the contractor then should use the data for, and what is the value is being created here? The value here is actually to have the knowledge and to act based on this knowledge. So this is, for this project here, this is a decision tool. The overall goal is to run at the same speed, even though that it's not a temporary bridge. And they're using the data, the digitalized monitoring, to actually know when to take care of the tampering process, to reduce risk for derailment, but also to increase the comfort for the passengers. So this is the purpose for this project, and what they actually used it for. It is in this case, this was I think it was a 4-month project where they installed this temporary bridge, and now they are having this permanent bridge again, and they do not monitor this transition zone anymore. But this is a way to make sure that the ballast is supporting the rail good enough. So now I will stop sharing my screen and go back to the presentation again. One thing that we also mention here is that the sensors that was installed, as you saw before, in the here is that the dynamic track deflection is very important. Lucky-wise, and maybe also what was expected is that the voiding, even though that there are voids, and they also was more or less sure that this was the case. But the good thing here is that the voids are equally on each side. So they do not have this imbalanced dynamic track geometry. So they have an equal movement of the sleeper, meaning that there's no risk of any derailment. Might impact the passenger comfort, but it would be very bad if there was no deflection on one side of the track, and then there was maybe 15 millimeter on the opposite side, because then you have like a twist, dynamic twist, and this is very easy to see from the data here that this is not the case. As said before, when you are using the trackbed 360 monitoring platform, the digital service platform, you do not need to have a look every day. Of course, it's very easy to get access from a web browser, but we have some different alerts that of course are being sent by either SMS or email to the relevant people who subscribe for these messages. We are able to set up notification and alerts for if things are stable and you have a sudden change, which means that even though that you have not reached the limits for sending what we call a thresholds alert, we're able to notify, because the software continuously monitor the data, and if things are suddenly changing, then you will get a notification saying, well, there might be something you need to look at. Last but not least, we also have some machine learning algorithms that are being trained on historical data, and from these historical data, it's possible to actually look into the future, see how the data would behave based on the historical data. And we have what we call a forecast lens function. And based on this forecast lens function, we're also able to make notifications. So if the forecast lens would see that we are approaching a threshold, then you'll get a notification up to 7 days before. So this is a quite good function that both the contractor but also infrastructure owners are quite happy about. So these are different I would say, intelligent functions that are built in into the system. So I think that was the speech from my side. If you have any other questions also afterwards, you feel free to write us the questions, and we will answer this as well. Then I will go back to the presentation here.
Yes, thank you very much, Niels. Thank you very much, everyone, for all your questions. And as Niels said, of course, we will be happy to answer more questions. Please just get in touch with us. We would like to just let you know that we have already planned to do another webinar. The next one will be on Tuesday, November 11th. Same time frame from 9 to 9:45 in the morning. And the topic at that time will be landslide and slope monitoring. And as you know, we see events all over the world, basically, that of the landslide type, which make slope monitoring quite important. And so we would like to get into that topic the next time. I think that's it. So at the last, thank you very much for participating, and we hope to see you again next time. Have a nice day.
Thank you.
Bye.
Take care. Bye.